So, good afternoon. Today we will be discussing the last topic from fifth unit. Okay. Before that, as usual, we will be discussing a positive thought, that is, find your purpose, your passion, your unique place in the world, and fight for it. I think this is the right time for the right semester for you. At least now you have to find your purpose of life, which job you are passionate. Okay, your passion and your where you should be, and then you have to work for it. Okay, so with this thought we will start today's lecture. So in yesterday's class we were discussing about radial basis function. That is the last topic from this unit, which is nothing but RBC, RBF, okay, RBF network, okay, radial basis function network. So this is very, we have already used this RBF in SVM. SVM, if you see, the kernel or the function which we have used is Gaussian kernel function or RBF function. So this already we have used before itself, but since the topic is there, we will be discussing this in a very detailed manner. Okay, so what is the topic is, first one is the radial basis function RBF is developed by MG de Powell, and there are sigmoidal as well as Gaussian kernel function, and normally we will be using this is more famous because due to it is used in regularization network, and that's why Gaussian function we will be Gaussian kernel RBF is this. Okay, so the shape of kind of a bell or something we could say, so this shape. Okay, so this is the shape of Gaussian kernel, whereas sigmoidal all of you know that it is in S shape. So Gaussian kernel only we will be focusing now. The function is f of x equal to e raised to minus x square, and the derivative of this function is f dash x, which is derivative if you take minus 2 into e raised to minus x. Okay, so it should be x, it should not be that's true, it is the same thing. So e raised to minus x square is f of x, so it will be minus 2 into f of x. So this way you can understand what is the kernel, and then radial basis function network. So in this network, what you have to understand, there will be there are three what I could say layers, in which the first layer is input layer, output layer, and the middle layer, which you could see here, is nothing but the RBF layer. Okay, so that is the hidden layer. So this is there is for all input existing within the fixed radial distance from the center of the kernel. That's why we call it as radial basis function network. Okay, then next one is the radial basis function can be the input layer, we call it as input activation layer, is mostly linear activation. So here the linear activation will be there. Even in output it will be the linear activation. So the middle one, whatever this which is the RBF layer or hidden layer, there is a difference between this looks like a multi-layer perceptron, but there is a difference. In multi-layer we can have more number of layers, hidden layers I mean to say. Here only one hidden layer. So this hidden layer functions are non-linear, and non-linear functions like, what are the functions? Gaussian, sigmoidal or biquadratics, and some more. Okay, that we'll discuss. This is the network is also called as localized network. Okay, localized receptive field network. Now we will go with the covers theorem, because RBF is based on this theorem. Okay, now the next one, what we have discussed in yesterday's class, we can do the if I am doing with a single line, this is called as, this is phi, that is RBF function is separable with the help of different dichotomies. The linear dichotomy is this, with the help of a line. Then there is spherically separable, with the help of circle I am able to separate it, or sphere or spherical shape. Okay, next one is with the help of um, quadratically separable, because it's like a parabola shape. Okay, so with the help of it we'll be able to separate. So these two are 1 and 2 are of same class, and the rest are, all are in the other class, like that. So if you draw one more circle, inner circle is one cluster, another one is another cycle. With the help of this is one group, this is another group, like that we can convert. Okay, so then next one, Macaulay theorem. So according to theorem, we are having three functions. Okay, three more functions we could say. One is like multi quadrics. This you should know. Okay, phi of r, that is the function. Okay, the radial basis function that are recovered or that are covered by Michael's theorem, it includes the following function. What are the functions that is covered under this theorem? So that also can questions can come. One is r square plus c square square root for c greater than 0, r belongs to the R space. The next one is, it is inverse multi-quadrics. Inverse, the moment I say, it will be 1 by of this. So 1 by, you can see that 1 by square root of r square plus c square for the same condition. Third one is Gaussian function, that is phi r is equal to expression or exponent, I mean to say, minus r square by 2 sigma square, where r is the radius, sigma is the standard deviation, sigma square is the variance. Okay, so with this you can see the same formula here. Okay, Macaulay's theorem. Now with this we were saying different shapes. I think we have reached in yesterday's class till here. So okay, so the diagram or the graph which you could see, that we will just have a very quick drawing. So first one is multi quadric. It's commonly used, this bold, this one green color. Then we will go with the inverse of that. Inverse of that, if you observe, this is the inverse of that. So this is belongs to this. Okay, inverse matrix. Third one is Gaussian. I'll take with the red color. Okay, so in Gaussian you can see that this is Gaussian. Okay, and there are few more you can see that which is with different colors, that is welland and thin plate, etc. So that with different colors that you could see. Okay, so this is one, this is another one, like this. Okay, these two. Okay, so you should not focus that, but minimum these three you should know. Okay. The radial basis function is a real valued function, and whose value depends on the distance from the origin. So the important of today's lecture is we are having practical based on this. If you don't understand this, you will not be understanding what practical we are going to do. So phi of r is equal to, that is radial basis function, equal to phi of r. What is this? This is, we call it as norm of magnitude vector r. Or alternatively, we can also say that on the distance from some other point called C with a center C. So if the from it is center C, then we will be representing phi of RC radius to center. Then that time the function will be norm of R minus C. Okay, so any function phi that satisfies the property phi r equal to 5 norm r is a radial function. So radial function ka condition is it should satisfy this condition. Important. The norm is usually, whenever I say norm, means it is a Euclidean distance. Although other distance or functions are also possible. There are different other distance functions which is possible, but commonly norm means Euclidean distance. Okay. Now next one very important point which you should understand in terms of theory or oral or understanding point of view is comparison between MLP and RBF. What is MLP? Multilinear or multi-layer perceptron. Okay, and RBF is radial basis function. Ye dono look like very similar, but in RBF we will be having only single layer. In all the three cases we will be having suppose I am taking 2 2. Okay, so this is actually a multi-layer perceptron, as well as this is this can be, so this is the output, so this is the input. So input layer, hidden layer, and output layer. So this can be a MLP as well as this can be a RBF. But RBF may strictly one layer. MLP have one or more layer. That is fine. Next one, the nodes of MLP in the hidden or output layer share the same neuron model. Okay. On the other hand, the nodes of RBF in a hidden layer play different role than the output layer. आउटपुट लेयर में जैसा है वैसा नहीं रहेगा, इधर डिफरेंट रहेगा. व्हाट इज द मेजर डिफरेंस? आरबीएफ लेयर इज, दिस वन इज नॉन लीनियर. मैंने क्या बोला है? दिस इज लीनियर, बट मिडिल लेयर इन आरबीएफ इज नॉन लीनियर. द आउटपुट लेयर इज लीनियर. Typically MLP, in an MLP both layers are non-linear. Both hidden layer as well as the output layers are non-linear in MLP. Okay, just an MLP. Now RBF network computes an argument of its activation function, that is Euclidean norm of the input vector and the center of unit. In MLP network, the activation function will be computing the inner product of input vector and weight vector. That is another major difference. Then the fifth one is MLP are global approximators. RBF are local approximators due to the localized decaying Gaussian function. So local approximation, if we need it, we will go for RBF, whereas for global approximators, we will go for MLP. So this is what you should know, the basics or the comparison of MLP and RBF. Any doubt till here? Anybody is having? Okay. Then we will move RBF, network. This will be, for classification it can be used. In RBF, we have concentrated on RBF networks for, further explanation. They are useful for classification problem. Consider a data set that fall into three classes: class 1, class 2, and class 3. Okay. MLP would naturally separate these classes with hyperplane. Hyperplane means with the help of some, plane. Plane का meaning is something like this. Hyperplane means something like this. Okay. इसके ऊपर there will be one class, maybe इसके नीचे there will be one class. Like that we will have different hyperplanes. With the help of line I am drawing it. With the help of this hyperplane we are separating the classes. So this is MLP. Whereas the model by localized radial functions, that is, this is with the help of RBF. So with the help of localized radial functions, we'll be able to classify this. This is the major difference between RBF and MLP. Okay, we'll go with the next point, which is real world application of this RBF. Okay, so if you see, we are having many applications. So one of this is, one successful RBF network is detecting epileptic form artifacts in the EEG recording. I hope all of you know EEG, correct? So in EEG there will be epileptic seizure detection. Okay, suddenly the brain will get damaged or kind of stop or something, that sort of thing. So that detections can be done. Early detections and everything is working on, people are working on. So that can be done with the help of this RBF. Okay, this is the example of how exactly. So what are the things that is needed in EEG? We need weighted histogram filter, zero level saturation, low amplitude saturation, and low amplitude, the high frequency contamination. Okay, these are the four pre-processing that is needed before applying to this. And RBF neural network, if you see, this is the input layer. In input layer, what are the four parameter that is taking? Weight histogram filter, zero level saturation, low amplitude saturation, and high frequency contamination after pre-processing. After pre-processing का meaning ऐसा है कि when I take an input, there can be noises and everything, so that will be cancelled and then it will be given as the input to the network. Okay, then we will be giving this network, this is the hidden layer. What kind of activation functions which we have used, or what kind of functions which we have used here is Gaussian. Okay, then Gaussian, that is RBF, it comes under RBF. Yes. So this is the hidden layer, in which after that the summation and then classification will happen in the output layer. Okay, so for full details you can see this original paper, waveform detection of RBF application to automated EEG analysis. Neurocomputing is a very good engineering branch in which a lot of research is happening in this area. So those who are interested can think about it. So this is a good application for using RBF, real world application. Now we will go with the RBF programs, okay, which we have to discuss. Before going to that, I would like to show you one more in the MATLAB. Okay, MATLAB you will be having, you can go and directly search in the help file radial basis approximation. Okay, latest one which you are having this option. Okay, this example is using new RB function to create radial basis function network. Okay, the radial basis network that approximating a function defined by a set of data points. So what this is doing, defining 21 inputs p and associated targets, because radial basis function kaisa hai, it is supervised learning algorithm. Okay, it comes under supervised. So inputs will be 21 inputs rahega, but uske sath kya dena chahiye, we have to give t, which is the target. Okay, so input and the target is given. So you can see that when I execute, you can see such kind of training vectors which is of shape this. Okay, input vector p versus the target, input versus the target. So we are getting a shape of like this. We would like to find a function which fits 21 data points. One way to do this is radial basis function. So this looks like a sine waveform or something, that sort of waveform current. So radial basis function network with two layers, a hidden layer of radial basis function, that is neurons, and the output layer of linear neurons. Here the radial basis function transfer function is used by the hidden layers. So we are having a function RADBAS. So actually what is that or how it is working? So you can just take it, either you can press F1 or you can take it and go here and you can search it. So there are, so normalized behavior. So this is the radial basis transfer function which is available. Can you see that? Radial basis function. So what there are n comma fb. What is n? Radial basis is a neutral transfer function. This transfer function can calculate layers output from its net inputs. So how it is doing? N will be there. N is an S by Q matrix of net input column vectors. Okay, net input or net vectors. FP is the structure of function parameters. This can also be ignored. So you can see that the how exactly it is working, etc. Even in the example, you can plot a radial basis function like n comma a. A is the radial basis function, n is from this to this. You can plot this function. So similar way we are doing it a radial basis function plotting here. Can you see -3 to 3? So -3 to 3, we are plotting a radial basis function here. Now after this, the weight and the biases of each neuron in the hidden layer of the layer define the position and width of the radial basis function. Each linear output neuron form a weighted sum of radial basis function. So you can see that it will be adding each linear neuron form a weighted sum of radial basis function with the correct weight and bias value of each layer and enough hidden layer neuron. A radial basis functions can fit any function with any desired accuracy. So this example is a 3 radial basis function. So you can see that there will be 3 radial basis function. One in blue color, whatever the 3 blue color, those are 3 radial basis function. So it is ending with 0. This is starting with -1 to something like this it goes, and one more is there which is having the maximum at 0. Like that we are having, it is having maximum at -2 and +2 4. So I'll repeat, there will be 3 radial functions you could see here, that is with blue color the shape. Okay, one is having, you can see that this is -2, maximum. Okay, the next one will be 0 with maximum, next one will be 2 with maximum. Okay, so these three radial basis function with the correct weight and bias, we will be able to get the desired accuracy. So in this example, the radial basis function with blue are scaled and summed up to produce a function. Okay, in magenta color you can see we are able to produce another function. So weighted sum of radial basis function, how we have done that? We have taken x minus 1.5, x plus 2 and something like that multiplication. We have made some kind of or prepared some kind of or weighted sum of radial basis function with input p and output a. So with this we will be able to the function new RB quickly creates a radial basis network which approximates the function defined by P and T. What is P? P is the total number of inputs and T is the target. In addition to the training set, and that targets, the new RB takes the arguments and some squared goal and spread the constant. Meaning is, here you can see that when you say the sum squared error 0.02, that is our goal that we are setting, and the spreading constant we call it as 1. So net we will be calculating new RB. So new RB also you can search it in the MATLAB and see. Okay, there are 4 terms here. One will be X term, then target term, then the sum of squared error and the spread constant. So once we get this, to show the networks, replot the training set. How to do that? Simulate the network response with the inputs over the same range. Okay, how we can do that? That you can see that here -1 to 1, the same range we have got one output. Whatever we have got here, target is the red color, and the plus sign, whatever you see, those are the target, and output, whatever the actual value we are getting, is plotted here. So you can see that it is target versus output, almost it is matching. So this is how we can map with RBF. Anybody is having any doubt here? If you are not having any doubt, then we will go with the programming part of it. Okay, whatever I have explained now is an example for RBF. This is readily available in MATLAB. You can go through it. Now, which program we need to execute is this. We have to implement RBF, radial basis function, for exclusive OR gate. Okay, what is our priority, or what we have to do is we have to find out the exclusive OR. We have to implement exclusive OR gate. So for that, what I will suggest is, I have just prepared a slide and I have added even in this. You can see that. So what is radial basis function or RBF network? You can see that here. Let me just check. Okay, done. Okay, here you can see that there will be an input layer, there will be a middle layer, hidden layer, and there will be an output layer. Okay, single neuron I have taken. Now here there will be even bias. So normally we write phi, but in programming I will not be able to write phi 1, phi 2, because Gaussian hidden function. I will not be able to write phi in the MATLAB. So I have taken G1 and G2. Okay, and what is exclusive OR? You know that exclusive OR will be x1 and x2, then we'll be having 1 1 1 0 0 1 0 0, correct? So this is the input. The exclusive OR input will be for 1 1 it will be 0, for 0 0 also it will be 0, for all the other cases the output will be 1. That is exclusive OR concepts, right? Now what is this? This is 2 input. What are the 2 input? Pehle I can give 1 1. So what is the expected output here? Target is expected as 0. Target is 0. So if I am getting actual value as 0, then that is fine. Otherwise I have to update the weight. That's it. Okay, so there will be 4 pattern, input pattern. बहुत सारे लोगों को ये confusion होता है. That's why I thought I'll discuss this once again. X1 and X2 means 2 neurons. Okay, at a time I'll be passing 2. So 2, 2, 2, like that. How many patterns I'm having? 4 input patterns. So this is actually whatever the output which we know exclusive, or this is the target or the desired output. That should be compared with the actual one. Okay, so how exactly this is working? You can see that in Gaussian function, G is G of norms, x minus Ti. X is the input minus Ti is the target, is equal to exponential of that. Here we are having 2 neurons in the input, so it will be 2, I equal to 1 to 2. And what is this? This indicates, the, norm imposed on the function space. Now, Gaussian hidden functions we are having 5 1, 5 2. Instead of that, we will be writing G1, G2 in the program. So, e raised to minus x minus T1 and e raised to minus x minus T2 whole square, whatever. T1 and T2 are nothing but the center of it. So, whenever I am having, suppose this is one group, this is another group. So, I'll be having one center here, the other center there. So, the T1 and T2 are the center point. Okay, and norm is imposed on the function. Now exclusive or and x is the input, that also we know. Now we are coming to the program of it. The in program we have to find out. So there will be w1 w2. I'll just show you the diagram. There will be w1 w2 and bias. Okay, so here we'll be having different bias that will be found with the help of Gaussian function. Now we'll come to the program. So in the program, first I'll execute as it is. Okay, you can see that radial basis function is trained for exclusive OR. What are the inputs which we are giving? 1 1 0 1 1 0 0 0 1 0. Whatever the way you want, you can give in different ways. Okay, and the G1 and G2, okay, is nothing but the hidden layer function, okay, for the different neurons, neuron 1 and neuron 2. Okay, G1 and G2 we have got. Once we got G1 and G2, yeah, one more thing I will just show you. G1 and G2, if you observe here, okay, there will be G1 for this will be having 1 2 3 4, correct? So that 4 will be there here. So G1 ke liye 4 and for G2 also 4, and the last column, so this one what indicates this is G1, this is G2, and this is nothing but the bias for all. Okay, what is the target that we are setting? If suppose 1 1 है तो क्या रहेगा 0. For 0 1 it is 1, then 0 0 it is 0, and 1 0 it is 1. Like that we are having the target. So what is the expected output? After weight updation, I am getting the same output. Actual output and the target output are same. Then we can say that the weight updation is done perfectly fine. Okay, so this is the output which is expected here. Now we will discuss the program in a simple way. One, you could see that in radial basis function, that is RBF, the input is x, so that 2 inputs or 4 input pattern is given as are normal, and there will be 2 centers T1 and T2. What is the first center? 1 1, the other center 0 0. Now we will be finding out all the values. So you can even see that the complex AB, if I say complex AB, meaning is z equal to complex AB means z equal to a plus bi. So this way we will be representing. Now you can see that there will be P1, that is complex x1 x2. So I will be, what I am taking in all the cases, q only, that is x11 minus T1. T1 what is that? Center of that, comma x12 minus T12. Like that we will be doing it for all ones and all twos. centers, all these points. So, and after that we will be taking the absolute of that. What is that absolute of x? Returns the absolute value of each element. Okay, positive or negative, it will be always positive. And then we will be finding out G1k. That's why we are having four input patterns are there. So for G1k we will be getting, and that we will be displaying as G1. Similar way G2 will be we will be getting. After that, what is the next step is last for two steps. You can see that G is W1, W2 and bias. So if you observe, this is W1, W2 and bias, the last one. Okay, then how exactly we have to calculate that? G1, G2 and all biases. So if you observe the output, you can see that G1, G2 and all biases will be there in G. Now what we are doing with the help of this is we will be finding out, these are the algorithm that is needed. We'll be finding out the this is the target value, the inverse G dash into G into G dash. What is G dash indicates is transpose of it. Okay, if you observe that, that is what I have written here. There will be G1, G2, this one, that is W1, W2, B. What is the equation for this? This one will be G1 G inverse, that is inverse of G dash into G into G dash. G dash is G transpose into D. What is D? D is the desired output. Then we can find the radial basis function as D is equal to G into W. So that is the same thing we have done it in the program, G into W. So we will be finding out all W's here. How many W's will be there? W1, W2 and bias. So that we will be displaying. If it is less than 0, then it will be 0. If it is greater than 0, then it will be 1. Like this way we will be displaying the output. You can see that once again. Okay, W is minus 2.5027. This is like this, like that different W you will be getting, and we will be, with the help of it, this weight updation is happened. Once weight updation is happened, next one is we have to give the input accordingly, whether we are getting it or not, that we have to check. If you observe, the target value and the output value are same, 1 1 0 0 and 0 1 according to the input which is given. Input is given at the beginning, so you can change it and see. You can give all the time 1 1 1 1 and then you can train it accordingly, but all conditions can be given. So with this, the last practical only is remaining. RBF, this is the practical which we have to perform, is radial basis function, that is trained for exclusive OR. Any doubt anybody is having, then you can ask.